Hello everyone, let's take a look at our next problem. This problem was submitted by a viewer. It says it is definitely not a very easy problem and maybe not so mathematical, but it has a pretty surprising answer. And also you don't have to know any specific facts. An infinite set S has the following rules. 1 is in S, 2x plus 1 is in S if x is in S, and 4x is in S if x is in S. Count the numbers in S that are strictly less than 2 to the power of n. And then I'm given a specific case so that I can check my answer. When n is equal to 7, the answer is 33. Okay, they give a hint as well, which I'll ignore for now and maybe come back to later. So I have seen a couple questions similar to this. I recently recorded an attempt at the AMC 10. I haven't yet posted that video, but there was what I think is probably a simplified version of this question, and significantly simplified. For one thing, the set was not infinite. And I've also seen something like this in another YouTube video quite a long time ago. I don't remember if it was exactly the same question. I think I'm not sure exactly what approach to take, but what I'm going to start with is just, we're given that 1 is in S, and so in some sense we can generate a whole bunch of other numbers just by starting with 1 and then expanding up to see what other numbers are in S. I think we're going to start like that, just list off a few numbers that I can generate in that way, and see if I can find some kind of pattern in the numbers or common aspect that all the numbers have. So just a small point of clarification. It's not mentioned in the question, but I'm assuming that we're looking for a minimal set S, or we're considering a set S that is as small as possible and satisfies these conditions. Of course, the integers themselves satisfy this, but yeah, the question is only interesting if we're looking for a minimal set. So when n is even, these numbers here are all 2 to the n for even values of n, right? We have 2 to the 0, 2 squared, 2 to the 4, 2 to the 8. So at least when n is even, all I have to do is count all the numbers in this tree. Like for n is equal to 8, I just count all the numbers in this tree. And then, of course, we're looking for strictly less than 2 to the n, so we throw that out, and that gives us the answer. Because these numbers can never be equal. Like, if we extend this pattern down the tree, and if it's not clear how I made this tree, I'm just applying the rule to each of these numbers successfully. So, we have a binary tree like this. Each element on the left is the 2x plus 1. Why don't I finish out this row? So for n equals 8, we have 1 plus 2 plus 4 plus 8 minus 1. So that's 14. Sorry, this is not for n equals 8. Wait a minute. They said, though, that when n is equal to 7, the answer is 33. Oh, this is, wait. This is not for n equal 8, that's 2 to the 6. Sorry, this is for 2. N equals 6. So there's 14. For n equals 8, that's for this row. So it'll be, in this case, 14 plus 16. Right? 1 plus 2 plus 4 plus 8 plus 16 minus 1. So that's, but that's 30. What am I mixing up here? 256 is equal to 4 to the 4, which is equal to 2 to the 8. Count the numbers in S that are strictly less than 2 to the n. So the ones less than 2 to the 8 are these ones and higher. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. How could the answer be 33 when n is equal to 7? These numbers, I think I was saying earlier, and I interrupted myself, the numbers in this tree will never appear more than once. And that's pretty obvious because, you know, we're alternating. Is that obvious? Hold on. I don't want to... I don't want to eat my own words here. Is it obvious? Of course, if you go down the left branch, you always end up in an odd number. If you go down the right branch, you end up in an even number. I don't see any in my example here already which repeat. Can we... And what is 2 to the 7? 2 to the 7 is equal to 128, right? Now we kind of get jumbled up because the numbers in the numbers in each row are not in order, so we can't just split the tree nicely in any way. When n equals 7, the answer is 33. I don't... So I don't know if I'm doing something which is a really silly mistake, or if that statement in the message to me is incorrect, that the number of the size of S when we're less than 2 to the 7 is 33. That can't be possible because I've counted that the ones less than 2 to the 8, there are 30 numbers. So what I'm going to do is I'm going to read the hint that's given and see if maybe I can come up with a new idea. Okay, so the hint says that I should look at the binary representation of the numbers. Okay. I'm going to rewrite the... I guess what I'm going to do is I'm going to reconstruct the tree using the two rules for the left and right, but I'll do everything in binary so that maybe I'll see a pattern that way. Okay, so when I multiply this by 2, I get 10, and then add 1, that gives me 11. 1 times 4 is just 100. Okay. Oh, crap. How do you multiply by 2 in binary? Do you just add a 0? Yeah, you just add a 0. Okay. So on the left, we'll get 111 for adding 2x plus 1. Multiply by 4 is add 2 zeros. Yeah. Okay, so here we go, add a 0 and then flip it to a 1. 1, 0, 0. Okay, so yeah, and then add 2 zeros. Okay, so the rules in the binary string are, if you go down the left branch, you just put a 1 at the end. And if you go down the right branch, you put 2 zeros at the end. Okay, and 2 to the n in binary, oops, don't know what happened there. 2 to the n in binary is 1 followed by n zeros or n minus 1 zeros. Well, 2 to the 0 is 1. Yeah, there are n zeros here. 2 to the 1 is 2. Binary representation is 1, 0. So there's 1, 0. Okay, so again, the ones, you know, for an even power of 2, we can just count numbers in the tree. Do the odd powers of 2, no, they can't possibly end up here because they all, let me think, okay. How do we figure this out for an odd value then? Okay, so I'm still not quite sure for odd values of n how to do this. I think this is the correct formula for even values of n. I'm still not sure why my answer for n equals 8 is less than the viewer's answer given to me for n equals 7. So for an odd value of n, I want to see if there's an easy way of identifying which numbers will be less than that. So here I've done it all the way up to n equals 6, right? This number here is 2 to the power of 6 because there are 6 zeros. So that is in fact equal to 2 to the 5 plus 1. And the only other numbers here greater than 2 to the 5 are this and this. So these underlined numbers here are all the numbers in the tree so far that are greater than or equal to 2 to the 5. So is there a way of figuring out for the odd numbers how often that happens? How often do we exceed? Okay, so if I go back to this tree here, these two numbers if we're looking for odd values of n, right? This here basically represents the row for n equals 8, right? This is 2 to the power of 8. These two numbers are both greater than 2 to the 7. This 129 is equal to 2 to the 7 plus 1. I'm not sure if I'm seeing an easy way of getting this. The binary representation, I don't think it totally helped. I mean, it was nice to see the pattern that you either throw 1 at the end or you throw 2 zeros at the end. But I don't see an easy way of identifying in the last row which of the numbers will be less than 2 to the n or greater than 2 to the n, whichever one, for odd values of n. I think I'm going to let this one sit for a little while. Maybe I'll come back to it. It's kind of an interesting question. Like I said, I've seen a couple questions like this. I've never remembered the solution. But it's usually, from what I do remember, they're usually pretty clever solutions on how to figure this kind of stuff out. So I'm going to come back to this one later. Maybe spend another few minutes on it in the next couple of days. But I'm confused. I'm confused about this, the inconsistency between what I get for n equal 8 and what I see the viewer has sent me for n equals 7. So maybe I'll respond to them about that first and ask for clarification. In the off chance that I end up not working on this anymore because I just never have any inspiration, I'll say thanks for watching. Check the description to see if I have any final thoughts or updates on stupid mistakes I've made. Okay, I'm coming back to this problem after letting it sit in my mind for a little while. I had a couple of spontaneous thoughts last night while I was falling asleep. The first is that I have found my mistake, and as usual, it's a pretty stupid mistake. So pretty straightforward. If we look at the case of n equals 6, so this here, 64, is 2 to the power of 6. It's clearly true that all of these numbers here are less than that, but there are clearly also other numbers in the next row which are also less than 2 to the 6. So my answer that I gave here is wrong because I was only counting the numbers that sort of were less than 2 to the n, but also appeared before 2 to the n in my tree. I wasn't looking at rows deeper into the tree, so I was underestimating. Now, my other thought is that I had another approach that I'd like to mess around with. It has to do with this binary expansion, and in some ways, we're looking at sort of a more combinatorial approach to the problem. So I'll try to illustrate my thought here for the case n equals 7. For 2 to the 7, that's where the viewer who submitted the problem said that the answer to the question is 33, so maybe I could verify that my approach does come out with the correct answer in that case. So let's first write down in binary what 2 to the power of 7 looks like. Okay, so a 1 followed by 7 zeros. This is 2 to the power of 7. Now we're looking for all of the numbers that we can construct with this process of, in binary, the two operations that we can do to create new numbers in the set are to put a 1 at the end of the number or put 2 zeros at the end of the number. And we want to look for all of the resulting numbers we can get which are less than this. So the first thing that's going to be important, if we want something strictly less than this, in fact, let me write this in aligned with the grid so it's easier to count the numbers that are appearing here. So if we want the numbers that are less than this, it's going to start with, at most, a 1 in that section. And then what I have here, I have 6 spots to play with, basically. They could be filled all with ones, or I could remove 2 of these ones and replace them with 2 zeros. So I want to think of the digit 1 and the pair of digits 00 as being individual objects, and I need to look for all arrangements of 1s and 00s that sort of fit into 6 places. So that's the general approach I want to take here. I don't know exactly yet. I haven't thought yet about how I want to set this up. So I think I might just play around for a little bit until I get something that makes sense, and then try and explain the thought process behind what I've done there. Okay, so I think I have worked out a recursion in terms of a recursion where, you know, every time we increase n, I count how many numbers we add to our list which are less than 2 to the n. So what I've done here, for the case of n equals 7 again, we have 6 spots to play with, and I parameterized the number of ones that are going to appear in all those spots, and also the number of zeros that are going to appear in those spots. Now, you don't, like I said before, you don't replace a 1 with a 0. You have to replace 2 1s with 2 zeros, but those 2 zeros have to be together. They have to be adjacent. And I believe, I mean, it's just a combinatorial thing. If they're all 1s, then of course there's only one way to do this. If there are 4 1s and 2 zeros, the number of ways to arrange those are going to be 5 choose 1, because you basically think of this as being 5 distinct objects that you're trying to order in some way, and one of those 5 objects is the 00. If there are 2 1s and 2 pairs of zeros, then you have 4 places that you can put things, and 2 of them are going to be the 00. And so there's 4 choose 2 ways of doing that. The general formula here is given by this. So n minus 1 represents the total number of spots that you have to play with, and m is the number of 00s that are going to appear in the arrangement. And so for every 00 that you have, the number of total spots you have to play with effectively decreases by 1. And of course, the number of 00s you can put into n minus 1 spots is at most n minus 1 over 2. So I don't know if there's going to be a way of simplifying this. Maybe I'll start by working out the value of this. So Cn is the thing we're actually asked for. I'm saying Cn is the number of numbers in the set that are less than 2 to the n. I'm not sure if there's going to be a simple way to simplify these things, but maybe I'll, again, just play around with some of the expressions and see what I can do. And I think I'll also compute the first few values of Cn. Certainly I'd like to verify that this formula works up to n equals 7, given the answer that was in the message to me. Okay, so I have verified now that the formula works. At least I manually counted all the numbers for the case n equals 6, and there are 20 of them that are less than 2 to the 6. I haven't counted for 7, but the formula does now agree with what was given in my original message. And as I went through these calculations, I don't think the recursion is exactly the best way to formulate what's happening here. We're adding up a whole bunch of, we're basically just adding up a whole bunch of numbers that appear in, what is that tree called? All these combinatorial arrangements. So for n equal to 1, the answer is 0. Then for n equal 1, the answer is 1. For n equal 2, the answer is 3. And we keep, after this, we just keep adding. So for n equal 4, wait, what did I say? This is for n equals 2. For n equals 3, we're going to add 2 to the 0, or 2 choose 0 and 1 choose 1. In each row, we're just going to be adding, starting with, the next number, choose 0, and then as we're going to add, but both simultaneously increase and decrease the top and bottom number in these combinatorial formulas. So I think, we will hit every pair of numbers in the combination formula. It's just a question of sort of where we draw the line. So you see we have, everywhere here we'll have, these are n minus 1. Or is it n? Just a minute. I've got like an off by 1 index thing going on in my head. Okay, so for n equal 1, there's only one number in the set less than that. For n equals 2, there are 2 numbers in the set, and that's this plus this. For n equals 3, the answer is 1, 2, 3, 4. Is that correct? One, 2, 3, 4. Right, those are all the numbers there that are less than 8. That's for n equals 3. And that's what the formula there gave me. For n equals 4, we add up this row as well. So this gives us another 3. 1, 2, 3, 4, 5, 6, 7. So it's 7 in total. So in this column here, I'm going to track the total sum. 4, 7. And here I add 1 plus 3 plus 1. 5, that's 12. So I want to see if I can figure out which of these combinatorial arrangements kind of get chosen out of the bunch. It's like a, what is the tree? Is it Pascal's tree? Where you're adding up all of the possible results of this combination arrangement. But we're kind of adding them up in a lopsided way. So first we get that, then we get that, then we want to get that. And then we want to get that. And then, nope, not that. And then we want to get that. So in each I mean, there's a formula, there's a simple formula for the sum of any triangle like that. Any if we have a complete triangle, there's a simple expression for it. Powers of 2 or something like that. Or is it 2 to the n plus 1 minus 1, I think. But so in each, I'm going to draw another row of this tree. Okay, so that's what we're looking at for n equal 5. And then for n equals 6, we're going to add those in. And for n equals 7, we'll add those in. So yeah, like at this point we can compute it easily, again, numerically for each value of n. I don't see an efficient or nice closed form way of like adding up this Pascal's triangle in this sort of skewed way. I think I might just have to leave this one. I mean, I'm moderately happy with this formula. It did allow us to get the right, it's correct. At least I'm pretty sure it's correct. It doesn't allow us to compute this number for a single given value of n without computing it for all the lower ones. I don't know if I just don't see a clean way of writing out the sums of these combinations when they're not really organized in the typical fashion. I'm not really sure. If I have more thoughts about this in the future, I'll add it to the description. So check the description to see if I do come up with an idea for how to do this. Otherwise, thanks for watching.